We would like to find a way to factor the Hankel matrix in the Ho-Kalman algorithm to be able to find the observability and controllability matrices in some good way, good yet to be determined what we mean by good. And in linear algebra, there's any number of ways that are taught on how to factor matrices of different types of matrix decompositions. Here we're going to look at one that's called a singular value decomposition, or SVD. And this is a fact, stated without any proof, that any rectangular matrix A, which has m rows and n columns, where rank A is some value r, can be factored into a form A equals U sigma V transpose. So we take one matrix A and we write it as a product of three other matrices. U is a matrix, and so this is first column of U is U1, second is U2, dot, 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 last column is U sub R. So U is an M by R matrix, such that U transpose U is the identity matrix. And the vectors Ui are known as the left singular vectors, or the output singular vectors of the A matrix. V, which we can also write as a bunch of columns from V1 through VR, is n by r in dimension, such that V transpose V is also equal to I. And the vectors V sub I are the right singular vectors, or the input singular vectors of the A matrix. And lastly, sigma is a diagonal matrix. It's zero everywhere except on the diagonal. And on the diagonal we have positive numbers from little sigma 1 through sigma r that are ordered such that sigma 1 is bigger than sigma 2, which itself is bigger than sigma 3, etc. All of them are strictly positive. And these are called the singular values of the A matrix. This is a compact SVD. And another way of writing an SVD is a full SVD. A little bit different. And this, if we have again our A is an M by N matrix, computes a U, which is not R wide, but it's M wide, where M is bigger than or equal to R. V is not R wide, it's N wide, where N is bigger than or equal to R. Again, we have these orthogonality properties of U and V, though, orthonormal properties. And sigma is sort of diagonal. Sigma, though, has to be rectangular in size for the product to work. And so sigma could be a wide matrix, it could be a square matrix, or it could be a tall matrix. If sigma turns out to be a wide matrix, then we have the first block section is a diagonal matrix containing the values sigma 1 through sigma m. If it's square, then it's going to have sigma 1 through sigma n, and if it's tall, then it's going to have sigma 1 through sigma n on top of a bunch of zeros. In this case, we have sigma 1 through sigma r are strictly positive, as they were in the compact SVD, but there are some possibly extra entries here to fill up the diagonal where sigma I is actually equal to 0. The SVD that is computed by MATLAB is the full SVD, and it can be computed using the svd.m command, or, as we'll see, there are benefits, or well, there's times when we need to compute only a portion of the SVD, so SVDS will compute only that portion, saving some computation. If I were to write the full SVD in a partitioned form, I would get this: A equals U1 as a block matrix with U2 next to it, and then I got V1 transpose with V2 transpose underneath it, and then sigma 1 and a bunch of zeros in this matrix, then the compact SVD is that and that and that, and everything else in here is 0, and everything else in here is chosen to be random, but random such that it still meets the orthonormal properties of U and V. So we can compute a singular value decomposition of a matrix. And by the way, it's not just MATLAB that can do this. There's very efficient routines to do this in Numeric Recipes in C, which is a very popular book for implementing algorithms, and in other books of that same nature as well. SVD is not actually difficult to compute, but it's not the focus of this course to teach that. So if you want to know how to do it, then I encourage you to go off and look at some of those references. Why is the SVD useful? Well, we begin to approach that by stating that the singular values of a matrix are related to the norm of that matrix. And we write the norm of matrix A to be equal to the maximum singular value of matrix A. Now a norm, we actually have it written below, but the norm of a matrix, norm of A, is equal to the maximum value of AX divided by X. And we usually think of a 2 norm there. So what is the maximum energy in an output vector of A times X divided by the energy of the input vector, or normalized by the energy of the input vector X? You could imagine that with some types of inputs, the output A times X might be small. Other types of inputs, it might be very large. And in fact, the maximum gain factor of a matrix is sigma 1. This singular value decomposition can be helpful in allowing us to visualize what happens when we compute y equals A times X by substituting y equals U sigma V transpose times X and looking at the operations that happen. So we start with X, and then we multiply X by V transpose to get V transpose X. We multiply that by sigma, and then we multiply the final thing by U in order to get AX. And because of the orthonormal properties of V and U, it turns out that the operations that they are performing is a kind of a rotation. So the first thing I do is I take X and I rotate it in some space along so that I'm computing coefficients of X along these input directions V1 through VR. And V1 is the most sensitive input direction. It has the highest gain overall, and the last one, VR, is the least sensitive. It has the lowest gain overall of all the input directions. Once I have computed the components along these input directions, I multiply them by this sigma I. I scale them by this sigma I. So if sigma I is positive, in fact, and greater than 1, I'm making it bigger than it was to begin with. And if it's between 0 and 1, then I make it smaller than it was originally. But there's some kind of gain factor along each one of those input directions. And then after I do the scaling, we reconstitute along the output directions U1 through UR. And U1 is the highest gain output direction. We could say that A times V1 equals sigma 1 times U1. That is a fact. The SVD then gives us some picture of gain as a function of the input and output directions. And that can be really interesting to explore how a matrix multiplication works in that way. An example that looks at this a little bit says, consider a square matrix A, which is 4 by 4, and I compute the singular value decomposition, and I get the four singular values 10, 7, 0.1, and 0.05. I'm not stating here what the U matrix and the V matrix are, but we'll talk about them in terms of their components. So input components along the directions V1 and V2 are amplified by 10 and 7 respectively, but something on the order of around 10, and they come out mostly along the plane spanned by U1 and U2. Input components along the V3, V4 directions, however, are attenuated. They're multiplied by 0.1 and 0.05, so they're attenuated by a factor of about 10. Overall, the gain of the operation A times X can range between 10 and 0.05. That's the meaning of those singular values. And furthermore, A is non-singular because its minimum singular value is not 0. Because we have two directions at the input that are high gain and two that are low gain, and the span between them is a factor of almost 100, we could say that A is effectively rank 2. It is a rank 4 matrix, but we could say it's effectively rank 2 or close to rank 2, or maybe I can find a rank 2 approximation to A that is going to produce almost the same results as the rank 4 matrix A. And that's critical for us, it turns out. If I form my Hankel matrix in my Ho-Kalman algorithm, I would, in some cases, end up with a system that is of very high order, but it's effectively a very low order. So if I can find a way to find an approximation to that Hankel matrix that is a low order approximation that still works really, really well, that is a very valuable insight. That's something very valuable to do. Let's look a little bit more at this. Let's look at low rank approximations. Suppose that A is some rectangular matrix in general. It's M by N. It's rank R. It has singular value decomposition, U sigma V transpose, which, by the way, we can write as this summation form as well. It's the sum from 1 to R of that singular value times that input that output direction times that input direction transposed. We want to approximate the matrix A with a different matrix A hat that has the same dimension, because I need to still perform the operation y equals A times X. So it has the same dimension, but it has a lower rank. And so it has rank P instead of rank R. So that in some sense, A hat is similar to A, and in particular, such that the difference, the norm difference between A and A hat is minimized. Well, it turns out that the optimum rank P approximator is A hat is the sum from I equals 1 to P of the singular values of A. Comparing these two, the difference is that I'm keeping the most significant P singular values instead of all R singular values. The difference then between A and A hat is the terms that I did not include in my approximation, which are the terms from P plus 1 to R, and that forms a new matrix having singular values, as it turns out, sigma P plus 1 through R. And the maximum singular value of this result is sigma P plus 1. That's the maximum remaining singular value, which is the gain of my error matrix. So that's the norm of my error. So the optimum approximator of A has kept the highest singular value because I don't want that to show up here. It's kept the next highest, the next highest, the next highest, and it's kept all of them down to some level where I'm able to accept sigma p plus 1 error in the norm of the error matrix, because that is, compared to what I've kept, this is negligible or not as important to me. So an interpretation then of the SVD is that the dyads, these pairs of UV transpose, are ranked in order of importance in the sense of the norm of the error matrix that remains when I make an approximation. I take the first P of these dyads to make the best rank P approximate to my original matrix. We can use this idea to simplify models, and this is very useful. Suppose that y equals ax plus v, and this v is a kind of a noise or disturbance value. And A is a big matrix. It's 100 tall, 30 wide, and it has a bunch of singular values from starting at 10, so 10, 7, 2, 0.5, 0.01, etc., and they just get smaller and smaller down to 0.00001 is the minimum. If we say that the input to this y equals ax plus v is on the order of 1 in norm, and the unknown error or noise v is on the norm of 0.1, then keeping all of these components down here is pretty worthless because they're going to be swamped by the noise. So terms that look like this for 5 through 30 are substantially smaller. So I might want to keep 1, 2, 3, 4. I may or may not want to keep that one. In this case, we're saying let's just keep the first 4 of them. Okay. All of the other are smaller than the noise term. So we can approximate y equals ax plus v by this simplified model of y is the sum for I equals 1 to 4 of these terms, all times x, so all of this multiplies x plus v. The structure of this matrix is simpler. I think that is clear. The computational complexity may not be obviously simpler at this point, because if I pre-compute a hat, it's the same size as a, so a hat x and a x are both have the same number of computations, but I can actually compute things within the sum to make it a little bit easier actually, so we can actually reduce computation that way. But this does have other benefits, and when we apply this to the Ho-Kalman problem, we will see that we definitely want this idea of simplifying our models by knowing what the singular values of our Hankel matrix and the Ho-Kalman algorithm are. That's what we return to next, now having some understanding of the singular value decomposition, and we proceed with our derivation.